Hi everyone, my name is Zheng Yan. I'm honored to present the COINDEF, a joint work with Simon Tran, Jizhou Chen, Rinzi Zhang, Brandon Sotomayor, and Winky Li. Before introducing COINDEF, I'd like to tell you a story of a real-world exploit. This is an Electron-based chatting app. The attacker tricked the customer service agent into clicking a malicious link he sent. Subsequently, the agent's device was infected with an exploited 2K. The attacker gained access to the company's internal network and stole 300,000 USDT.
Why was this attack even possible? The answer lies in the unique features of Electron-like platforms, which support popular daily drivers such as VS Code, Evernote, and Slack. Electron and similar frameworks are designed to provide a seamless desktop application experience by bridging web technologies with native system capabilities. To achieve this, as demonstrated in the figure, they expose powerful APIs that allow the UI side, which is typically built with web technologies, to interact directly with the underlying operating system. While this makes applications more functional and responsive, it also introduces a major security risk. A simple code injection attack on the UI is no longer just an UI issue. It can escalate into a full-fledged remote code execution. This means an attacker can exploit even a small vulnerability in the front end to gain control over the entire device.
To address these issues, we introduce a key idea, enforcing the abstract syntax tree, or AST for short, as a security mechanism. Why? Because any injected code will ultimately modify the AST. If an attacker injects malicious code, it will change the structure of the AST, introducing a new or modified subtree that wasn't part of the original program. Let's look at the example in the figure on the right. Here, we have a vulnerable piece of code that uses eval to colorize the console output. A legitimate input, such as red, yellow, or blue, is treated as a data node in AST. The structure remains unchanged. However, a malicious input can inject a shell command instead of a simple color name. When this happens, the injected code is parsed into a new subtree highlighted in the red. This structure change indicates an injection attack. So by enforcing AST integrity, we can prevent these attacks. The idea is simple. We allow the changes only to the values of the existing data nodes, which accounts for the legitimate user input. And a structural modification, like a new subtree, indicates a code injection attempt and can be blocked immediately.
Now, a key challenge is that we have two different execution environments, the web and the native. So, how do we secure them both simultaneously? The answer lies in a single choke point, the JavaScript engine. Look at the figure on the right. Because every piece of JavaScript code, whether benign or malicious, must pass through its interpretation pipeline. It does not matter whether the code is executed through DOM manipulation in the browser or dynamic code execution in a native environment. The JavaScript engine processes them all. This gives us a perfect opportunity by instrumenting the JavaScript engine, so we can enforce AST integrity at the source before the injected code ever executes. Even better, this approach comes with minimum performance overhead. Since JavaScript code is passed only once before execution, enforcing security checks at this stage is essentially a free ride, introducing negligible runtime impact. Beyond just blocking injections, this method also allows us to capture the valuable execution context, such as which process is running the code and where the code originated. This lets us apply context-aware constraints on the AST modifications, making attacks even harder.
To enforce AST integrity effectively, COINDEF operates in two phases. Before enforcing security, COINDEF first learns how the application behaves by collecting AST profiles as baselines. It observes the application at runtime, analyzing AST node structures, including node types, positions in the tree, and values. Since some AST modifications are legitimate, such as user inputs influencing code generation, COINDEF allows changes only in the values of data type nodes, while blocking structural modifications that could indicate an attack, as discussed just now. To collect the profiles of an application, COINDEF takes a hybrid approach, which I will discuss later. Once profiling is complete, COINDEF switches to the enforce mode. It verifies the runtime context before verifying the AST structure, including process information, color identity, and call site details. By doing so, COINDEF ensures that code execution aligns with expected behavior, blocking any unexpected AST modifications that could signal an injection attack. To handle exceptions, COINDEF follows predefined security policies, which result in two enforcing modes, security first and the usability first. I will discuss that in detail later. To evaluate COINDEF's effectiveness, we tested it on 20 real-world applications, including high-profile ones such as VS Code and MS Teams. These applications were chosen because they represent the most prevalent code injection attack surfaces, covering a wide range of real-world vulnerabilities, including all types of cross-site scriptings, client-side open redirect, prototype pollution, etc. In these applications, the injection points generally fall into three main categories. The first is the chatting messages, where the attacker's network request or victim's network's responses can be manipulated to execute an intended code. The second is remote content, such as the untrusted web resources that could introduce malicious scripts. The last one is markdown files, where the seemingly harmless text, but actually can be coded with HTML code, so that they can be used for code injection. By testing COINDEF against these diverse attack scenarios, we can assess its ability to prevent real-world code injection exploits while maintaining the application's functionality. Before we can evaluate COINDEF against the real-world attacks, we first need to collect AST profiles for each application. To do this efficiently, we use a hybrid profiling approach that combines static analysis, dynamic interaction, and manual efforts. COINDEF builds its AST baselines using three key methods. The first is static scanning. We develop a customized command line interface for the VA engine to invoke COINDEF and statically analyze JavaScript code before execution. The second is dynamic interaction, to simulate the real user behaviors and explore possible execution paths. To do this, we leverage the end-to-end UI testing cases that can automate the interactions. Then we develop the intelligent crawlers that navigate through the application, triggering the JavaScript execution. Lastly, we supplement those approaches with manual efforts in cases where those automation isn't enough. We human testers interact with the applications to reach a convergent state. When we say convergent state, we mean no matter how we exercise the application, the covered path no longer increases. The time required to collect the AST profiles varies depending on the application size. For large applications, it generally takes around 4 hours to reach convergence. For applications with a robust end-to-end testing cases, it only takes a couple of minutes. For simple applications, 30 minutes is enough to achieve a full profiling. This hybrid approach ensures comprehensive AST coverage while minimizing the overhead, preparing COINDEF for accurate and effective enforcement. Once we complete the AST profile collection, we enter the enforcement mode for each application. To test its real-world effectiveness, we used these applications as part of our daily workflows for an entire month. This meant coding with VS Code, messaging with Slack, and interacting with various applications just as any regular users would. To assess how well COINDEF monitors and enforced AST integrity, we measured function-level code coverage across all applications. Small applications reached full coverage, while medium-sized applications maintained over 90%. Even medium to large applications achieved around 80%. And for the largest applications, and they are more complex, the coverage remained at 70%. Across all applications, COINDEF achieved an average coverage of 87%. These results demonstrate that COINDEF effectively enforces AST's integrity in a wide range of real-world applications. To truly test COINDEF's effectiveness, we evaluated against the real-world attacks. We collected 20 documented attacks from the cited sources. Additionally, we designed 59 attack variants trying to evade COINDEF's protection mechanism. In security-first mode, COINDEF successfully blocked all attacks, achieving 0 false negatives. This means that no real threats were able to bypass its protection. However, this strict enforcement mode also led to some false positives, where legitimate features were mistakenly blocked. In total, we observed 17 false positives. Among them, 12 came from chat applications, primarily due to third-party remote content, and 5 occurred in VS Code, specifically when application attempt to update itself. Handling code update is straightforward. COINDEF can quickly reprofile the updated portion of the application when the application signals there is an upgrade needed. This can ensure the legitimate changes are recognized. However, remote content poses a bigger challenge. Since third-party remote content is unknown during the learning phase, there is no completely effective way to allow it without introducing risks. That said, we argue that this limitation is reasonable because users can still manually access remote content by clicking the links and opening them in the browser, like demonstrated in the figure at the bottom.
In usability-first mode, COINDEF prioritizes minimize disruptions while still enforcing security protections. Under this setting, it produced 0 false positives, meaning even third-party remote content was allowed to run as intended. However, this flexibility came with a trade-off. We observed 2 false negatives in chat applications, where attacks were able to execute successfully. Despite this, the impact was limited. These attacks were confined to an isolated execution environment, following our predefined security policies. To further evaluate the system's resilience, we attempt escape techniques, trying to break out the isolated environment and execute injected code in a more privileged first-party context. COINDEF immediately blocked the code as soon as it attempted to enter the first-party execution space. This demonstrates that even in the usability-first mode, where some attacks might initially execute, COINDEF still prevents them from causing real harm, ensuring that critical applications logic remain protected. We recommend this mode to users who want to enjoy features that frequently load remote content, such as those chatting apps. To assess the performance impact, we measured its runtime overhead across different applications. Since COINDEF operates within the JavaScript interpreter, it only introduces overhead during the script pausing, that is, when the code is first loaded and analyzed. Once the script is paused, COINDEF does not add actual runtime checks during execution, ensuring minimum performance impact. The chart on the left illustrates the impact on the application startup time. As you can see, 19 out of 20 applications have less than 1% runtime overhead. Only one application, which is Discord, resulted with less than 9% overhead, but the absolute value is still less than 1 second. This slight delay occurred only when the application is first launched as COINDEF profiles and validates the initial code execution. The table on the right highlights that during normal user interactions, there's no measurable runtime overhead. Once the code has been paused and verified, COINDEF does not recheck it upon execution. This means that users experience no noticeable slowdown when using the applications. These results confirm that COINDEF provides strong security protections with minimum performance trade-offs, making it a practical solution for real-world applications. Thank you. There's some more details in the paper. You are welcome to contact me for any questions.